Okay, today we will be doing the third lecture on integrated assessment models and the social cost of carbon. This will be estimating the social cost of carbon, and we will talk a bit about discount rates. So we have defined the social cost of carbon. We've outlined what an integrated assessment model is. We have looked at the basic equations in the DICE model, the integrated assessment model we will be using in this class. And today we will estimate the social cost of carbon. We will download the DICE model in Excel and we will run it. But first, let's talk about how, in theory, we would estimate the social cost of carbon. So we define the aggregate social welfare function as before. So if we look at this slide here, it's welfare, which is a function of consumption and labor. But this is discounted welfare, where 1 over 1 plus r is the discount factor raised to the time period t. Time period is going to be in years in the DICE model. And we are summing the discounted utility all the way up to the end period. I think the end period in the Excel version right now is 2150, 2150, the year 2150. So note this is the discounted sum of utility over all time periods in the model. For example, let's do a 3 time period example. Suppose that the per period utility is given in the following table. Time period 1, 2, and 3. Emissions are going to be 10 in each period. So this is just an example. It's unitless. Labor is 1 in every period. The discount rate is 5% in every period. And consumption is 2, 3, 4. Consumption is increasing. And suppose the utility function is just given by C plus L. All right, well, let's calculate the first period utility. So C plus L is going to be 2 plus 1, which is 3, and then discounting that to the first time period, so discounting by 5%, that gives us a utility of 2.86. And the Excel model is going to do this for you, but this is just in principle what's happening. The second time period, the utility is going to be 3 plus 1, consumption plus labor is 3 plus 1, which is 4, discounting 1 over 1 plus 0.05 squared. That's going to give us a value of 3.63. In the third period, the utility is going to be C plus L, which is 4 plus 1. So the utility is equal to 5. And discounted to the third time period, that's going to result in a utility of 4.4. So the welfare function just sums up from time period 1 to 3, sums up those discounted utilities. So 2.86 plus 3.63 plus 4.4 equals 10.8. We're going to maximize this welfare function. The mathematical definition of the social cost of carbon is the change in welfare over the change in emissions over the change in welfare over the change in consumption. So a small change in consumption affects welfare, and a small change in emissions affects welfare as well. If we do a little bit of hand waving, we can say that this is approximately equal to a change in emissions affects consumption. So this is what we're estimating, the social cost of carbon. How does a marginal change in emissions affect consumption over all time periods? So in words, the social cost of carbon is equal to the ratio of the change in the stream of discounted welfare given a change in emissions in period t to the change in the stream of discounted welfare given a change in consumption in period t, or in practice, it is equal to the change in the stream of discounted consumption caused by a change in emissions in period t. So this is the a change in the stream of discounted consumption. All those consumption in all the time periods going forward, discounted back to the present period. How is that affected by a marginal change in emissions today? The interagency working group is the group primarily tasked with developing these models and running them and figuring out what the social cost of carbon should be for the United States. They are the ones, so on modules there are readings from them, There's a description of how they actually went about calculating the social cost of carbon. They're the group that estimates the social cost of carbon for U.S. policy analysis. Here's how they did it. They used the three integrated assessment models that we looked at. They used DICE, FUND, and PAGE. Step one is you enter a baseline path of emissions, GDP, population, etc., and you run the models to calculate year-by-year paths of temperature and per capita consumption. So we're going to do that. That's just the baseline, what the model comes out of the box looking like. And then we will shock the model with 1 additional ton of carbon emissions in year T, where year T in our case is going to be the base period, or today, and we will recalculate temperature and consumption paths. So that's going to be going back to step 1 and seeing how that shock in emissions in the first period propagates through the model all the way to 2150. How does that affect consumption today, tomorrow, the next day, etc.? So it's important to remember that we're looking at a change in emissions today affecting consumption all the way out through the end of the model, end of time in the model. We aren't changing emissions today, tomorrow, the next day, etc. We are only changing emissions in the current time period, the beginning of the model. So we want to find out how a marginal change in emissions today impacts consumption all the way out into the future. And we're going to discount those effects back to today's values. Step 3, compute the marginal damages in each year as the difference in per capita consumption estimated in step 1 and step 2. So we will subtract consumption in the baseline model. We'll subtract the change in consumption from the shock in the emissions from the baseline consumption, and that'll be the marginal damages in each period. And then we will discount the resulting path of marginal damages back to the year of emissions shock and calculate the social cost of carbon as a net present value. And this is what you will do in the simplified DICE model. Okay, so for example, here's our the same example we had before, but now we are actually looking at how emissions are going to change and how that's going to result in damages. So emissions in the baseline model are 10 in every period. So we have T equals 1, 2, and 3, so 3 periods again. Labor and consumption are the same, 1, 2, 1, 1, 1, and 1, 1, and 1 for labor. The discount rate's the same, 5%. Consumption is 2, 3, and 4. Now in red, we are going to shock the emissions in the first period with 1 additional ton of emissions. So we're going from 10 to 11 in the first period. Notice that emissions in the following periods do not change. We're going to have 10 units of emissions in period 2, in period 3 still. So how does consumption change? In this simplified example, consumption declines from 2 to 1.9 in the first period because of the shock in emissions. In period 2, consumption declines from 3 to 2.9. In period 3, consumption declines from 4 to 3.9. So the change in consumption is going to be 0.1 for every period. So this is the marginal damages in every period. The marginal damages being the loss in consumption from a shock in emissions in the first period. So the marginal damages in every period in this simplified example is 0.1. And then finally, we want to discount the per period marginal damages. So we'll discount each of those marginal damages and then sum them up. So in this case, the sum of these marginal damages is 0.27. So the social cost of carbon in period T, we should actually say this is period 1 because that's when we shock the model. In period 1, the social cost of carbon is the sum of discounted marginal damages, which is equal to 27 cents per ton of CO2. Now, of course, that's very low, but this is just an example, and we'll see that it's higher in practice. So here's the graph from the interagency working group of the distribution of the social cost of carbon estimates. using different discount rates. A discount rate of 5% in green, a discount rate of 3% in blue, and a discount rate of 2.5% in red. So the average for a 3% discount rate is $42. The average for a 2.5% discount rate is $62. And these have a distribution because there's uncertainty in the parameters in the dice model, and also the expected paths of labor and other things in the model. So what they do is they kind of like how Bornstein, Bushnell, and Wolak estimated the distribution of marginal costs in the electricity markets. Here, the authors are estimating a distribution of social cost of carbon estimates based on uncertainty. So they're running a Monte Carlo simulation. So now I want to give you a quick tutorial on how you're going to actually run the dice model. On Canvas in modules, at the very bottom, you'll see that you have access to the dice model already. So you can download this. This is an Excel dice model. So go ahead and download that and open it up. I will also post the first assignment pretty quickly. So the first assignment, instructions and assignment, is going to give you information on how to estimate the dice model. So you can watch this video, but also you will run this assignment. So the first assignment, you'll be estimating the social cost of carbon using the baseline model. Tell me what you get. Estimate the social cost of carbon after changing the sigma decline rate, which I outline how to do below. And then change something else in the model and re-estimate the social cost of carbon. So this is basically what you're doing in your final paper and in your presentation, but we're just getting up to speed on the model. So I give you sort of a tutorial on what the social cost of carbon is here. Then I tell you how to calculate the social cost of carbon, how to optimize the model, so you will have to run Excel Solver. This is how to optimize the model, how to calculate the social cost of carbon. Please make sure you follow all of these steps. Please make sure you look at these steps and follow them very closely. You cannot skip steps in here. If you skip steps, you will not calculate the social cost of carbon. Every year, people come to me and ask, why do I get a negative value of the social cost of carbon? And I say, did you follow these steps? And they say, no. And I say, well, that's why. So please follow these steps that I've outlined here. Okay, so let's look at the Excel Solver version of the DICE model. When you download the model, this is what it looks like straight out of the box. So we've got some notes at the bottom. We've got parameters that you can change. I've highlighted the key parameter that you're going to be changing. This is the initial amount of emissions, and so this is what you're going to shock. So remember that the interagency working group shocks the emissions with an additional ton of CO2 in the first year. This is where you're going to change that. So the initial value is 8960. We'll change it. I'll show you in a minute how we change that. We have the baseline model. So this is the model. Now if you go into the slides that I gave you on the equations in the DICE model, you can actually trace back the equations in this spreadsheet to those equations in the PowerPoint slides. So you can click on these and find that there's an equation embedded in all of these cells, and those equations are the equations I gave you in the in lecture 2 of the DICE model. So let's calculate. We also have the optimal tax. So Nordhaus gives you the optimal tax, limiting to 2 degrees C, the Stern, the Copenhagen, and then some graphs. So these are the graphs of the outputs. All right, so let's let's talk about how we would actually go about calculating the social cost of carbon. The first thing you need to do is download Solver. Actually not, you don't even download it, you add it in. So you go to File, Options, and here you should be able to go to Add-ins, and then you find, click on Solver, Add-in, click on Go, and make sure that you click Solver Add-in and push OK. And then it should show up over here. When you click on Solver, so it's on the Data tab, you click on Solver, it should already be programmed what needs to be solved. So the objective is cell B129. This is the discounted utility. That's cell B129. This is the welfare function. So remember on the slides we talked about the welfare is the stream of discounted utility. This is the sum of discounted utility in this model. This is the welfare function output, and we are going to maximize this. So make sure you have your solver set to maximize and not minimize. We're going to change the variable cells. These are the cells that we are maximizing over, B131 to AD131. And then we have some constraints. So don't change any of these constraints. These are just there so that the model gives you reasonable results. It's setting a constraint on what the output could be. All right, we want to estimate the social cost of carbon. So we're going to do that by following the instructions in this assignment here. The first thing you want to notice is that you have a baseline per capita consumption. This is the, so if we go back to the slides, you could see that the baseline per capita consumption is before we've shocked the model with an additional ton of CO2. And then we have new per capita consumption. This is going to be what happens after we shock the model. And then this line here, which is all zeros right now, this is the difference in consumption between the baseline and the new. So this is going to be marginal damages. And this equation, or this cell here, is going to sum the discounted marginal damages back to the present value. And here's our discount rate. So right now it's set at 3%. So let's figure out what the baseline social cost of carbon is in this model without changing any parameters. Okay, so to make a change, we're going to change the initial value. We're going to shock the first period emissions with an additional 1,000 tons of emissions. So I'm going to go 9960. The reason I do 1,000 is because I want it to actually show up in the model. If I do 1 ton of emissions, then you can't really see any changes. It's so small, the model. The model notices it, but it's out in decimal places, and it's more interesting to see what a 1,000-ton shock does, and we will account for that when we calculate the social cost of carbon. So I'm going to shock the model with an additional 1,000 tons in the first period. And let's go back to the baseline. Okay, so you'll be focusing primarily on the baseline tab and the parameters tab. You can look at the other tabs, but this is the one that we're primarily interested in. I leave the other ones in there in case you want to go further with this and see how limiting CO2 or limiting temperature increases to 2 degrees C, for example, is run in the model, or how we would find the optimal tax. So here's the baseline. Now we want to, well, it's already programmed into this, so we can resolve the model after we've shocked. After we shock the first period with an additional 1,000 tons of emissions, go ahead and resolve the model. You always have to resolve the model. Give it a second. So I paused it while it was solving, so you didn't have to sit there and wait. So it says keep solver solution or restore original value. So we're going to keep the solver solution because that's That's what the output is. We don't want to restore the original value. So now we have the baseline per capita consumption, what we had before, and we have a change in consumption, the new per capita consumption from an additional 1,000 tons of emissions in the first period. So the first 3 periods, the change in consumption is negative. In other words, with an additional 1,000 tons of emissions in period 1, we're actually doing better. We're consuming more for 3 periods. But after that, the consumption declines. The consumption is negative. The consumption is still positive, but the change in consumption is, we consume less. And we're going out to AD in this model, column AD, which is year 2150. All right. So the present discounted value of the marginal damages is going to be this cell here. So each of these values should be discounted. Each of the values in row 141 is discounted back to the current period. So you can see we have the change in consumption, F139 minus F140 over 1 plus the discount rate to the time period. So that's going to give us the discounted marginal damages, and we're going to sum those values up and divide by 1,000 because we shocked the model with an additional 1,000 tons of emissions in the first period rather than 1 ton. So the baseline social cost of carbon in this model is $19.25.5. Now let's go ahead and change something in the model and see how that affects the social cost of carbon. So let's write down first, the baseline is $19.25.5. So now let's change something. The assignment has you changing. Let's look at the assignment. The first step is always reset your baseline emissions to 8960 in cell C50 in the parameters tab. Okay, let's first reset the baseline emissions. We always want to start with our baseline emissions, 8960. Go back to the base tab. Okay, so then let's resolve the model. Always want to resolve the model. Okay, so I've resolved the model. I'm going to keep the solver solutions. I'm going to take the new per capita consumption because this is what Excel has given us as the solution. I'm going to copy and paste this entire line into the baseline per capita consumption, but I'm going to paste the values. So the baseline per capita consumption here. Paste the values, and then I can start over. Now the model's back to where we were. Now let's start over and change something and see how that affects, see how our change in some parameter in the model affects the social cost of carbon estimate. So in the assignment, I'm having you change the decline rate of sigma. Sigma is CO2 per GDP. So this is how this sigma value evolves over time. So that parameter is in, or that value is in the parameters tab in cell B57. Set this cell to -0.1. So let's go to cell B57 on the parameters tab. Here's the parameters tab. B57, decline rate of sigma per year. Right now it's set at -0.001. I asked you to set it to -0.1. So for this example, I'll do it at -0.01, just to not completely give you the answer. Let's take a look at what that did. Okay, so that gave us a social cost of carbon, but this isn't quite right. We haven't resolved the model yet. We haven't found the welfare maximizing solution. So we have to, every time we make a change, we have to resolve the model. So let's do that. Resolve the model. Okay, the model's solved. Now we're going to keep the solver solutions. What this did was it changed the new per capita consumption. So I changed this line here. So the social cost of carbon right now is nonsense. Don't think about it as a value that means anything. In order to estimate the social cost of carbon, we always have to do this step where we cut the new per capita consumption and paste it into the baseline per capita consumption, but we paste the values. Okay, so now we have a baseline per capita consumption with a change in the decline rate of sigma. So we always have to think about what is our baseline. Our baseline isn't the model that's out of the box. It's the model that we have changed. The model where we've changed the decline rate of sigma from negative 0.001 to negative 0.01. And the shock to the model, what's going to change our new per capita consumption and give us a difference here, or marginal damages, is going to be the change in the emissions. So anytime you make a change to the model, anytime you make a change, not the emissions change, but you want to change a parameter and see how that affects the social cost of carbon estimate. So in this case, we're changing the sigma decline rate. Anytime you make this kind of change to the model, you have to update the baseline per capita consumption. You have to start with a baseline per capita consumption that is what you get after you've solved the model, having made the change and leaving the emissions at their initial value. So now we've done that, we have a new baseline per capita consumption. Now let's shock the model with an additional 1,000 tons of emissions in the first period. Now let's resolve the model after we've done that. Okay, Excel found a solution. We're going to keep the solver solutions. Now we have the baseline per capita consumption with a sigma decline rate of negative 0.01 instead of negative 0.001. We've shocked the model with an additional 1,000 tons of emissions. That updated the new per capita consumption in this line. And now we have marginal damages, the difference between these two in this line, discounted to the present period. And then we sum those up and we get a social cost of carbon estimate. So this is the social cost of carbon estimate with a sigma decline rate of negative 0.01. The baseline model out of the box had a sigma decline rate of negative 0.001, and we had a social cost of carbon estimate of $19.25. Now with a sigma decline rate of negative 0.01, the social cost of carbon estimate goes up to $24. So we've added an additional $5 to our social cost of carbon estimate simply by changing this sigma decline rate. So that's what you're going to do in your assignment here. So I give you the steps. Go to the base tab and run the solver given the changes you've made after you've changed the sigma decline rate. Copy the values from row 140 and paste them into 139. Make sure you copy and paste the values, not the formula. Then shock the model with an additional ton of carbon in year 0. That's how we went from 8960 to 9960. Go back to the parameters tab and find the baseline industrial. That's where you do it. Re-optimize the baseline model by clicking back on the base tab and rerunning the solver, and then the value in cell B142, the base tab, is the new social cost of carbon estimate. In my model, I got $54. In the model you download, it looks like you're getting $24. So, so that's going to be the $24 for a sigma decline rate of negative 0.01. In your model, you're changing it to negative 0.1. So maybe we get $54 with a sigma decline rate of negative 0.1. So please, when I give you this assignment, please follow all the steps here. Figure out how you run the model, how you calculate the social cost of carbon. Make sure you're optimizing every time you make a change, and you reset the baseline every time you make a change.